Hi everyone, this is Kalyan Kumar this side and welcome once again to Chemistry Universe. In the last video, we did Alkynes Part 1, that was introduction and the preparation of alkynes. And in this one, we'll be talking about the physical and chemical properties of alkynes. Now, as I have repeatedly said before, it is very important to watch all these videos in sequence. So first watch alkanes, then watch alkenes, then watch alkynes, and everything in the same order. Because many of the times I'll keep referring back to the previous videos, what we had done before. So that is the first point that I want to make. And the second thing, as I again repeatedly say, do not watch this video like any other video you would watch on YouTube or in any website. You need to keep notes. So you need to see this video like a lecture. So keep your notes, keep your notebook, pen, everything ready. And while watching the video, make notes, pause as much as you want and watch them, but try to watch these videos in one shot. Don't, take a break in between, then come back, because that would break the rhythm, that would break your involvement in this particular lesson. So make sure that every video that you watch in this particular channel, you are giving your full attention to it. That being said, so let's start with the physical and the chemical properties of alkynes. So let's look at the physical properties first. The first one is quite trivial. First 4 members of the alkynes are gases. Next 9 members are liquids and the higher ones are solids. It's not necessary to remember all of them. The boiling points of alkynes are nearly the same as those of alkenes and alkenes because they're all hydrocarbons after all, with the same number of carbon atoms. Here, of course, when it comes to polarity, there is a bit of a difference. You see, alkynes are relatively less polar than alkyl halides. Now, alkyl halides or haloalkanes, there the electronegativity difference between carbon and halogen is much higher than the electronegativity difference between hydrogen and the carbon with the most electronegative hybridization, that is sp. Despite that, the CH bond, if it exists in an alkyne, is not as much polar as that of an alkyl halide. So alkynes are more like hydrocarbons, which is why, of course, we include them in hydrocarbons. They're more polar than alkenes and alkynes, but less polar than alkyl halides. Alkyl halides in turn are even less polar than alcohols. So this behavior is seen in their respective boiling points with the same with similar molecular mass. All right. So alkynes are relatively non-polar than alkyl halides and alcohols, but they are more polar than alkenes and alkanes. They're nearly insoluble in water. They're quite soluble in most organic solvents like acetone, ether, ethylene, chloride, chloroform, alcohols, etc. Now let's talk about the chemical properties. Now, though alkynes have higher pi electron cloud density than alkenes, they have an extra pi bond. They're less reactive than alkenes towards electrophilic addition reactions, and this is due to 3 reasons. Now, I've already told you when we were doing preparation of alkynes that the pi electron cloud of alkynes is more cylindrical in nature. If you remember, I gave you the example of the parachute, the glider's parachute, which is somewhat, bent. So imagine that the first pi electron cloud is on this particular plane, and there is a pi cloud electron on top and at bottom. This is one pi bond. Now, if you were to take the next pi bond, it will be in the perpendicular plane, which will be like this. So there is another parachute like this and this. So if you see the entire structure together, you'll find that the pi electron clouds are quite closed rather than open. So despite having an additional pi bond, we do expect alkynes to be more reactive, but they are not. They are less reactive than alkenes, but they are less reactive than alkenes for electrophilic reactions. Now this is very, very important. People make this mistake of saying, are they more reactive or are they less reactive? And since I just told you they are less reactive, we keep saying they are less reactive. You must understand something is less reactive not for every reaction. They are less reactive towards electrophilic reactions. In fact, you will know, and I'll explain later, this we've also done in alkanes, that alkynes are actually more reactive than alkenes when it comes to hydrogenation. Because hydrogenation is a reaction which is not electrophilic. It is a single step process in which the two hydrogens add. And we've discussed this in alkanes as well as in alkenes, that, alkynes being linear, it is far easy to get them hydrogenated than alkenes can be. So alkynes to alkenes are easier than alkenes to alkanes. So more reactive for hydrogenation, but less reactive for electrophilic reactions. So let's see the three reasons. One of which I've already told you is the nature of the cylindrical pi electron cloud. So the first reason is that the two perpendicular pi electron cloud make the overall pi electron cloud cylindrical in shape, causing loss in surface area. This offers less exposure to the incoming electrophiles. Now, another important reason is the fact that, it is not, how does an alkene uh, react with an electrophile? If you remember the reactions of alkenes, electrophile comes, the pi bond shifts to one of the carbon atoms and it takes the electrophile. What happens to the other carbon? It forms a carbocation. Now there the carbocation is sp2 hybridized. Whereas here the carbocation is sp hybridized because it is already having a pi bond. And if you remember from our previous lectures, I told you that a plus charge can be treated as a pi electron as long as far as hybridizations are concerned. So an sp hybridized carbocation is highly unlikely to form. It is highly unstable. Vinylic carbocations are not stable at all. And therefore, the ability to form a carbocation and then react with the nucleophile is not going to be possible because, first of all, the vinylic carbocation itself is not going to form. So that is the second reason for alkynes to be less reactive than alkenes towards electrophilic reactions. So electrophilic addition reactions are either through carbocation formation, like the addition of HX, or through three-membered bridged ring intermediates, like oxymercuration-Demercuration, and halogenation. So the second reason is that vinylic carbocations are less stable than the typical ones, as the carbon is sp hybridized and is more electronegative. Now let's look at the third reason. The third reason is that three-membered rings are more unstable if the carbon is sp2 because it would cause more strain. Now just imagine that you have a three-membered ring. Now three-membered ring itself is, if all the carbons were sp3 hybridized, even then it is less stable. But imagine if two of them were sp2 hybridized. How difficult it would be, to form a carbocation like C double bond C and then have some electrophile here with a positive charge. Now, how unlikely is this to form? I mean, here they want the angle to be 120. Because of the three-membered ring, it happens to be 60. Look at the deviation here. This deviation is far greater than the deviation if the carbons were sp3. I mean, from 109 to 60 itself is a big deviation. From 120 to 60 is far more deviation. So three-membered bridge ring is very, very difficult to form unless and until, of course, you have highly reactive metals, because metals, these transition metals, have lone pairs in them. And these lone pairs can easily, the advantage of a metal is that the metal is electrophilic in nature because it has empty d orbitals. It also has lone pairs, and through which they can form a quick three-membered ring intermediate, which would be highly unstable and which would be extremely prone to react in the next step with the nucleophile, which is why the alkynes can in fact react if you have some metal or metal ions acting as the catalysts. So because of this, many electrophilic reactions of alkynes require the presence of catalysts like metals that can relatively easily form three-membered intermediates due to the presence of the lone pairs that can also easily break open in the next step. And since hydrogenation, as I said in the beginning, is a non-ionic reaction, it occurs faster for alkynes. So to say that, alkynes are always less reactive is not fair. Now, hydrogenation we have already done in the case of alkenes and alkynes. We have said that you can convert alkynes into alkanes, and you can even stop it at the alkene stage by using certain catalysts like Lindlar's catalyst, etc. Let's look at the addition of HX. Now, addition of halogen acids to alkynes occurs in accordance with Markovnikov's rule. Addition of one molecule of halogen acid gives an unsaturated halide and then adds another molecule of hydrogen halide to form geminal and vicinal dihalides. Now, you will notice this quite often. All the reactions of alkenes. Now, why, by the way, this video is going to be relatively shorter than the reactions of alkenes, mainly because it is repetitive. Whatever I used to happen in alkenes once, here it will happen twice because there are 2 pi electrons, 2 pi bonds. So, to say therefore that, the reactions of alkynes are similar to alkenes, yes, quite true. For example, alkenes would react with 1 equivalent of HX. 1 equivalent of alkene will react with 1 equivalent of HX, whereas here 1 equivalent of alkene will react with 2 equivalent of HX because of the 2 pi bonds. So what will happen is the mechanism, one doesn't really have to go into the mechanism, just follow the Markovnikov's rule, and for both additions it could be Markovnikov. First it could be Markovnikov, then it could be anti-Markovnikov if you use peroxide with HBr. Or you can use peroxide with HBr first, then you do Markovnikov. You can do all sorts of things and we'll see all of them now. So HBr in the presence of peroxide shows the typical peroxide effect. So let's check this out. You have an alkyne here. I've deliberately taken this alkyne where you can use the Markovnikov rule because one carbon has one H, the other carbon doesn't have any. So what would happen if I were to first react it with HBr normally, and then to produce A, and then HBr with peroxide to produce B. Now, with A, if I were to add HBr, it gives me, let's say, C, and HBr peroxide gives me D. With B, I do the same thing. I take HBr and I get E, and I take HBr peroxide and I get F. So what I want you to do is I want you to pause the video right now and make the products A, B, C, D, E, F, all of them. And only then once you finish it, take your time, finish it, and then play the video back because now I'm going to give you the solution. So, all right. So first is Markovnikov's. Let's simply follow the Markovnikov's rule instead of using the mechanism. So what does the Markovnikov rule say? Markovnikov rule says that when you add anything to an alkene, the hydrogen will go to the carbon with more H, or the negative part will go to the carbon with less H. Obviously, this is H plus and Br minus. So H should go here and Br should go here. Let's take this out. Let's see what is A. Exactly, that's what is A. Since I added only 1 mole of HBr, so I'm getting this. So now that you have this, what would happen if I were to add HBr with peroxide? Now with HBr and peroxide, obviously it is going to form an anti-Markovnikov product. Now let's go back to A. Now let's see what happens when you add HBr to A. So this is A and I add HBr. So where will the H go and the Br go? The H will go to the carbon with more H. So I should get a geminal dihalide, and that geminal is on the middle carbon. And with peroxide, well, the opposite happens. I get a vicinal. With B, if you do the same stuff, you add Br and H. H will go to the carbon with more H. So H went to the right carbon and the Br went to the left carbon. And with peroxide, same stuff. I get the geminal. Now here the geminal is different because it is on the terminal carbon. So you're able to get all types of products here. And very similar to this is the addition of X2 in CCl4. I'm not doing the mechanisms because it's similar to alkenes. Now 1 or 2 molecules of halogen can be added to alkynes, giving dihalides and tetrahalides respectively. Chlorine and bromine add readily while iodine will take time. That we know about iodine. If you take chlorine, In CCl4, you'll get 2 Cls, then add one more, and then you'll get 2 more. So you get a tetrahalide. Similarly, let's look at addition of X2 in water. Now we know that one carbon will have the OH attached, another we should have the halogen attached. Reacts with hypohalous acid or HOX in the molar ratio of 1:2. That means one alkyne and two of them to give dihaloketones. Acetylene forms the dihaloaldehyde. This is what it means. You have this one, add Cl2 in water, Cl will go to the right and the OH will come in the middle, and you have one more molecule getting added, and you find this to form, and you know that carbon with 2 OH will lose water and form a carbonyl part. And acetylene, as you know, will be like this. So eventually you will get the aldehyde. You get CH-Cl2. This is what you'll get with the acetylene, which is why we say it's going to give you a dihaloaldehyde. Now, one may wonder, even though this is enol, why doesn't it tautomerize rather than add one more molecule of Cl2 in water? Well, there are not much reasons available, but generally it is said that since the lone pair of this is in resonance with the pi bond, the tendency to enolize decreases. So which is why it is not enolizing now. But in other cases, if there was no Cl here, if there was only H here, it will tautomerize and form the corresponding ketone. Which is what is the next reaction? Hydration, or also known as the Kucherov's reaction. Now, water adds to alkyne when alkyne is treated with 40% sulfuric acid containing 1% HgSO4, which is going to act as a catalyst, as I said, metal ion, to form a carbonyl compound. Now, there's a very funny story to this. It is said, we haven't confirmed it, but it is said that when this person was performing the experiment, he took the alkyne in an acidic solution, boiling H2SO4, and kept on boiling, and didn't see any change, didn't feel that the alkyne was reacting, and didn't know what was happening, but he kept on hitting it. And it reached an extent where the thermometer broke. The glass of the thermometer broke, and all the mercury in it fell down. And mercury, being a metal in a highly boiling acidic medium, it immediately converted to Ag2+. And when that happened, the reaction happened suddenly. That is how this person came to know that for this reaction to happen, the alkyne has to be treated with sulfuric acid as well as Ag2+. So let's see the reaction. So you have the alkyne here. Again, it's a Markovnikov addition. The OH comes from the middle carbon. And here, as you can see, since there is no halogen attached on the terminal carbon, it will easily tautomerize and form the ketone. The mechanism is quite similar to oxymercuration types. It forms a 3-membered ring. Not easy to form. With metals, it can form, but highly unlikely to form. And very slow step. But then the other step is very fast, because it helps break the 3-membered ring, and it loses the H plus, and you get this. And then you see you have one more H plus, and this bond breaks to give liquid mercury. This goes here, and you get Ag2 plus going here, and you get enol, and which will tautomerize. Similarly, you have OMD, Oxymercuration-Demercuration. You have the alkyne, and you do oxymercuration, then demercuration, and you will get this. Again, enol, you will get ketone. And similar to this is Hydroboration-Oxidation, anti-Markovnikov addition. So the OH will come to the terminal carbon. I'm not showing you the mechanisms, not required. And you get the aldehyde instead. Then we have addition of HCN. The addition of HCN in the presence of barium cyanide gives vinyl cyanide. Basically, one carbon will add the H, the other will add the CN. Then comes the addition of ASCl3. It's not a very good reaction in the sense that the product formed is has absolutely no use other than causing a lot of danger to the people doing this. In the presence of AlCl3 and AgCl2, acetylene combines with AlCl3 to yield leucide gas, which is extremely poisonous, sometimes used in wars. It is four times, in fact, four times more poisonous than mustard gas. So you find AlCl3 reacting, one Cl goes here and AlCl2 comes here. We call it 2-chlorovinyl dichloroarsine or leucide gas. Basically, what these gases, mustard gas, and what these do is they irritate the skin first. You will have a lot of itching. Then it will start forming blisters. And these blisters will be extremely filled with water, just like the blisters you get when you get burnt. And then it will happen all over the body. The more the exposure, more would be these rashes forming. Liquid leucides are actually more dangerous than the vapor ones. And if you were to inhale them, which you would in any eventuality, if it is, if there's a bomb with leucide gas exploding, you end up inhaling them. All of these blisters will start forming in the lungs. The person suffers extremely painful death. And it has been found that this particular compound has absolutely no other use, practically of no use, which is why it is banned, just like mustard gas. All right, so the next is the combustion reaction. Now we are coming to oxidation. Now this is basic normal combustion. This you can of course easily understand. And if I were to take an example, this would be the reaction. Now it is the reason I'm showing you with acetylene is because acetylene torches are formed because they give a lot of heat, highly exothermic, and you reach temperatures up to 3000 degrees Celsius, which is why it is used in welding. Then you have oxidation with cold KMnO4, the Bayer's reagent. Well, it's pretty simple. Here what happens is that the two pi bonds break, and for each pi bond breakage, you will get one OH on each carbon, and eventually you will get a diketone if it is a non-terminal alkyne. With terminal, you will get a ketoaldehyde. So non-terminal alkynes with cold KMnO4 give diketones. So sigma won't break because it is cold and neutral, and you'll get a diketone. With terminal alkyne, they first give aldehydes and then acid, because the aldehydes are very prone to oxidation and they will eventually form acids. But if you take hot alkaline or acidic KMnO4, you will get even the sigma bond breaking. You'll get one more OH, and eventually you will get two acids. And with terminal alkynes, of course, you get formic acid because that formic acid can further be oxidized to CO2. Then you have ozonolysis, of course, both types, oxidative and reductive. And here oxidative ozonolysis is like Bayer's reagent. It will give you a diketone. It doesn't break the sigma bond. Very surprising, because in the case of course, with oxidative ozonolysis, it will break. But with reductive ozonolysis, you used to get sigma bond broken, but not in the case of alkynes. Then you have a very interesting reaction, the isomerization reaction. In fact, this is the reaction for which I gave the definition of a non-terminal alkyne, an internal alkyne, and a terminal alkyne. Because this is the situation where you'll find a terminal alkyne converting to a non-terminal alkyne, which we defined as two alkynes, and the non-terminal becoming terminal. Internals are not affected. So when terminal alkynes are treated with alcoholic KOH, they give non-terminal alkynes. So alcoholic KOH, they give you non-terminal, and non-terminal can be converted to terminal by NaNH2. So when non-terminal alkynes are treated with NaNH2, they give terminal alkynes. Now here I need to make sure that you understand this, that one of the reactions of alkynes, rather the preparation of alkynes, we did the preparation, and in one of the preparation I did how to make a bigger alkyne from a smaller one. You take a terminal alkyne, you add NaNH2 to it, it takes the terminal H, acidic H, and then it forms C minus. C minus acts as a nucleophile. You take RX, it attaches to the R, X minus leaves. Now that you know that NaNH2 can also convert a non-terminal to a terminal, means that even a non-terminal alkyne with NaNH2 followed by Rx can give you a bigger alkyne. So just because you have an alkyne reacting with NaNH2 and then Rx and forming a bigger alkyne, that does not necessarily mean it has to be a terminal one. It could be a non-terminal one also. But it all depends on the options given. If you have only one answer correct and one of the options is a terminal, go for the terminal one. But if it is multi-option correct, then, and if you have the right terminal and the right non-terminal, go for both of them. Okay. So then comes polymerization reactions. There are many of them. First is dimerization. When two molecules of acetylene pass through a solution of Cu2Cl2 and NH4Cl, vinyl acetylene is formed. So this is what happens. And you will get a dimerization reaction. And the way the reaction happens is that Cu plus acts as the catalyst. First, one of the alkynes becomes a nucleophile. Then the other alkyne becomes an electrophile due to the formation of this three-membered bridge ring. And then the nucleophile attacks in the next step to this one. And then the Cu plus leaves, leaving a carbon ion, and to which you add some water or any protic reagent and you'll get the dimer. Now here, if you were to do this, what would happen? So I want you to check this out. I'll give you the answer. Just try to look at the mechanism. Now look at the product. Basically what I've done is I have removed the H from this one. So this is that part remaining, triple bond. And you can see the rest of the two are double bonds. That means this is attacking this. And where is it attacking? If you can see, it is attacking the carbon with the CH3. So it is attacking this. So this is attacking this one. And the bond is breaking. You are getting a double bond, which is why eventually you get two double bonds. So you get the nucleophile from here. The Cu plus forms the bridge ring and it attacks this carbon. Now my question to you is, alkenes are actually more reactive to electrophiles than alkynes that we know. So wouldn't it make more sense for this to attack the alkene rather than the alkyne? But it still attacks the alkyne. So I want you to first write the mechanism of how this is formed and then ask yourself what would happen if it is attacking here, then form the product and then look at these two and figure out why is it attacking the three-membered, the triple bond rather than a double bond. So this is for you to figure out. The next is cyclic polymerization, which is pretty interesting. When alkyne is passed through a red hot metallic tube, cyclic polymerization takes place with the formation of an aromatic compound. Like for example, this is a very, very important reaction. Red hot tube, you take acetylene, you get benzene. You take propine. Here you can get a variety of compounds, but the most stable one is this. You can get this also, You can get this also. You can get this also. And you can get this also, but this is more stable due to less steric hindrance. But if you take this, then obviously all of them will be substituted. Then of course, then you have linear polymerization. Hydrochloric acids add in the presence of Hg2 plus, you will form the vinyl chloride, which can be polymerized to give PVC. So basically HCl is adding, Hg2 plus is the catalyst, one H goes to one carbon, one Cl goes to the other carbon. And when you do polymerization, you will get this. Now in such polymerizations, you need to understand something. What we're meaning by this is that we are saying there is one CH2 attached to a CHCl, then a CH2 attached to a CHCl, and then a CH2 attached to a CHCl, and then it goes on, which is why we are calling this as a unit. Now you might wonder, why does it have to be exactly alternate? Why can't it be like CH2 with CHCl and then another CHCl and then CH2 attaching to a CH2, attaching to a CHCl, etc.? Why can't it be random? Well, remember, all of them are formed. So why are all of them not formed? Because only this is PVC. We are only looking at how PVC is formed, but others would also form. The same way you can add HCN. I would rather show you the reaction. This is called PAN. You get this, and if exact alternate adds, get this. It's called PAN, that is polyacrylonitrile. Similarly, with acetic acid, you'll get this. And if a proper polymerization occurs, you'll get this. We call it PVA, polyvinyl acetate. And then in the end, we get the test for terminal alkynes. Well, pretty simple. Terminal alkynes form precipitates with ammoniacal solution of silver nitrate, tolerance reagent, and copper 1 halides. So you can get this. This is a reddish orange precipitate. And if you take it with tolerance reagent, you get this pale yellow. Now it's very important for you to understand this, that tolerance reagent that I'm adding, even though it is giving a reaction, this is not the tolerance test. Tolerance test is formation of Ag, silver metal. Here you don't get a silver metal, you get a silver salt. So just because it is reacting with tolerance reagent doesn't mean it is tolerance test, number one. Number two, if you look at this one, we just did dimerization with this exact reagent. So you might wonder that since you are taking a terminal alkyne and you're adding the same reagent, why would it not dimerize and why would it form a reddish orange precipitate? But it's pretty simple. If you take this in excess, the reagent in excess, that means almost all of the alkyne will form this because you're taking the reagent in excess. You're not taking alkyne in excess. So all the alkynes will become this. So when all the alkyne becomes this, the ionic product becomes high, and if it becomes higher than the KSP, it will precipitate out. But if you want dimerization, remember in dimerization, we wanted some alkynes to form the nucleophile and some alkynes to form the three-membered ring. For that, the alkynes have to be in excess. So if alkynes are in excess, you will get dimerization. If the Cl2 is in excess, you will get the precipitate. And with that, we come to the end of this particular video. So I hope this video helped you in understanding the reactions of alkynes, and go through the notes. And if you have any specific questions, you can ask these questions in the comment section below. With that, this is Kalyan Kumar signing off. Have a wonderful and great day, and thank you for watching this.